You have the flip-flops, say if it is a 4 bit, so four flip-flops will be there. If it is a decade counter, I mean having 4 digits to indicate, then 4 similar count of decade count will be there. So anyway, that variation will be seen later on. So output here, digital output here will be available corresponding to the input, input signal, analog signal here, corresponding to this. B in star is the input signal which is sampled by sample and hold circuit, which is not shown here. It is shown just that one input B in is there, which is starred here to indicate that it is a sampled and hold signal, analog signal. We need digital output corresponding to this input signal. At the beginning of the conversion cycle, the analog input is sampled and held and applied to the positive terminal of the comparator, as you can see here. The counters are reset and clock is applied. Okay, here clock is applied, and before that counter is reset, this counter and this counter is reset. The reset signal is not shown here explicitly, but it is reset so that the output of the interval counter and this all are 0. What happens here? See that clock is applied here, which is applied to this interval counter as well as the AND gate. The clock will be getting path only when this is high. Other input of the AND gate is high. Otherwise, clock will not be going and counter will not count. When the first clock falls, the ramp generator begins to integrate the reference voltage Vref. Here you have applied the reference voltage Vref, and since it has been reset, so here output Vt is initially 0. Ramp generator's output, ramp is will be generated in this way linearly. It will be ramping up, but starting value is 0, and then it will keep on increasing linearly. So if V star is greater than the initial output of the ramp, if this is greater than this, then your output of the comparator will be high. Okay, and hence once it is high, then this clock will get path to the counter. Okay, clock will be available here in this way till it is greater. B in star is greater than Vt, clock will get path and counter will start counting from 0 and count up in a binary sequence. We know the counter, so its function is known to us. Finally, when the output of the ramp generator exceeds B star, that is the input analog signal, the output of the comparator goes low. It becomes low. Okay, it becomes low, and the output of the comparator output counter is now disabled. Okay, once this is low, 0, this positive input is this input is 0. One input is 0 okay. If this input is 0 or low, then this clock will not get path to this. I mean the output of the AND gate will be always 0. So count will stop counting. The binary number corresponding representing the state of the output counter can now be converted to the desired digit. The queues of these counters, remember that counter means it is having flip-flops, and the queue outputs of these counters are going to give you the digital output corresponding to this input. Is it understood? Shivam Shurana? Kartik Agarwal, yes or no? Nobody is listening?
Understood.
Understood? Okay.
Yes, sir.
The serial ADC has the advantage of simplicity. Its design is so simple. There is no problem in understanding this or designing this. The disadvantage of the single slope ADC is one weakness of the single slope ADC is its dependency on an extremely accurate ramp voltage. The ramp voltage which is going to be generated here in this way, it should be accurate. This in turn is strongly dependent on the R and C values inside this. Actually, this is the ramp generator. You have a capacitor and resistor. Well, we have seen this. It is nothing but an integrator. Okay. But if in an integrator, we know this equation we have studied while reading the operation of operation amplifier. We have studied that it can be used as a differentiator as well as integrator. In this case, it is integrator. For the differentiator, what should be the circuit configuration? Can anybody say? Anybody can say? For differentiator, what should be there? It is integrator. Can anybody remember? No. Shubham?
Sir, capacitor should be connected first, then resistor.
Yes, interchange the locations of the capacitor and resistor. Yes, you are correct. So if the voltage V in of this circuit is a constant, V in equals to D, for example, then the output will be a ramp, VO, and VO will be the ramp voltage in this way. It will increase in this way. Okay, equals to minus V by RC into T. Since B, R, C all are constant, this is an equation of a straight line that has the slope of this. Any difficulty in understanding this point? Integrator equation is there, which we have already seen. Integrator equation. If V is constant, okay, because you know this here, this is the circuit, ramp generator circuit we're talking about. It is going to generate the ramp. Your reference voltage is a fixed. The reference is a fixed voltage. So if V here is fixed, then is it not this integration value is this? Yes or no?
Yes, sir.
Okay, good. A negative sign comes because it is inverting configuration. So with this, we understand how the ramp is generated, and disadvantage what we understand is that the output voltage, ramp voltage here of this ramp generator is dependent on R and C, and we know that R value and C value will be, especially R value will be varying if temperature varies. Okay, so it is a problem. Okay, so dual slope overcomes this problem. It was single slope and having this problem because it was dependent on RC, and RC dependent means a ramp may not be accurately generated by the ramp generator. Once temperature is varying, the ramp may be not same minor room temperature. Is it understood? Another disadvantage is its long conversion time. If the output voltage is near the value of V in star, then it is because it will start ramping up from 0 and try to reach up to B in star. That is the analog signal which has to be converted into digital. So it will take a long time to reach up to that point. Okay. If Vn is very small, then no problem. It may take less time. Okay. The worst case conversion time is 2 to the power n into t, where t is the period of clock. The single slope ADC can have many different implementations. For example, the interval counter can be replaced by logic to detect the state of the comparator output and reset the RAM generator when its output has exceeded benchmark. Is it understood? Kartik Agarwal. Aman is there? Tripathi, Bushra Akhtar. Bushra Akhtar has dropped in this semester or not giving exam? Never I have seen. Anybody can say anything? So we'll go to the next slide and see. So this is what I was talking about in details. If you want to read what is RAM methods, etc., or single slope method, then you can read it out and try to understand even more. Up to this point, our interest in different method of analog to digital conversion has been centered on reducing the actual conversion time. If a very short conversion time is not a requirement, there are other methods which is called analog digital conversion are simpler and implemented much economical also. I mean to say single slope is considered as very simple, very simple to design and it is less costly. Okay. Single slope. We're talking about single slope, which we have already seen block diagram. Basically, these techniques involve comparison of unknown input voltage with a reference voltage that begins at 0 and increases linearly with time. This is what we have seen in the last. So it is comparing with the input signal and with the reference voltage. Reference voltage starting from 0 and increasing towards the input signal, that is B in star. The time required for the reference voltage to increase to the value of the unknown voltage is directly proportional to the magnitude of the unknown voltage. Is it understood? And this time period is measured with a digital counter. Actually, counter is, I mean to say, counter is doing nothing, but during that time when the ramp is getting generated and it is less than the B in star analog input signal. It is continuously counting up. Once the VT, that is the ramp value, is becoming equal or exceeding the value of B in star, your counter is stopped. The count time is converted into digital form. This is referred to the single ramped method. Don't be surprised if it is said single slope and sometimes single ramp method. It is same. In the reference voltage is sloped like a ramp. A variation on this method involves using an operation amplifier integrating circuit in a dual ramp configuration. The dual ramp method is very popular and widely used in digital voltmeters and digital panel meters. It offers good accuracy and good linearity and very good noise rejection characteristics. Okay. So we are now heading towards dual slope. We have seen the single slope and we have understood certain disadvantages of single slope. So to overcome this disadvantage, we can study the dual slope or dual ramp method. We'll now look at that. So what is the disadvantage of single slope? Can anybody say?
Long conversion time.
Yes, another thing. See, it is
Value of VT depends on RNC.
R and C. That is most important here. In single slope, the RC dependent is so in dual slope we'll see that it is not there. Conversion time will be here also longer. It is not going to be shorter in dual slope. Conversion time is going to be longer only, but it will not depend on RC. It is free from RC dependent. That's what we are going to see now. Still single slope, but here taken from different book, and here what is done is ones and tens and hundreds counters. I mean decade counters are cascaded in series, and in addition to not only the digital output in binary form, it is going to display it in 7/7 display. This is additional. The whole thing is additional, you can think of. But if you have this, then you can show the results also digital in the digital form, analog value in digital form. Possibly that is done by various vendors who design the digital oscilloscope or digital multimeter kind of things. Okay. So let's read out and try to understand what extra things if said by different authors, Millman and Rich. Let's take a look at this single ramp ADC in this figure. Figure is, it is same. If you look at it is same. The heart of the circuit is a ramp generator. That is on this one. This is a circuit that produces an output voltage ramp as shown here. Okay. The output voltage begins at 0 and increases linearly up to a maximum of Bm. It is going to reach up to Bm. It is important that this voltage be a straight line, and that is, it must have a constant slope. That is also we have discussed in the last slides. For instance, if Vm equals to 1 volt DC, it takes 1 milliseconds, for example, to reach up to this point. And this is the time. Time is here. 1 milliseconds for the ramp to move from 0 to 1 volt. The slope 1 volt per millisecond or 1000 volt per second is the slope. This ramp generator can be constructed in a number of different ways. One way might be to use a DAC driven by simple binary counter. Okay, then staircase kind of output indicating. This would generate the staircase output waveform. I mean to say, instead of this kind of things, you will get something like this. It will get like this. It is not sharp like this. Or you can say it is kind of sawtooth waveform. Something like this. In this way, to sawtooth waveform. We have seen earlier this kind of in the definitions section. The second method is to use an operational amplifier connected as an integrator, which we have already seen. Here also I have put for you. For this circuit, if Vi is a constant, the output voltage is given by the relationship this, and since Vi, R, and C all are constant, this equation is a straight line equation. Now that we have a way to generate the voltage ramp, and we understand its characteristic. Okay, so it is easy. You can put it in use. This one is what the ramp generator. Here is your analog input, which might be a sample and hold circuit. It is coming from sample and hold circuit. clock generator is generating clock and applying to this, which is now applied to the counter. Okay, there is a switch. If you press the switch, then it will be generating a reset, and the RAM generator will be reset, and the clock, counters will be reset, and then a ramp will start generating on the ramp in this fashion. And whatever discussed earlier, the same thing will happen. If it is positive, clock will be going. If it is higher Vx, higher than this ramp here, then this will be high and clock will be passing and counter will start counting in a manner sequence. The decade counter here. Yeah. So what is written here? The 3 decade counters are connected in cascade, and their outputs can be strobed into 3 flip-flops here. Decade counters will be having how many flip-flops? Decade counters inside the decade counter, anyone? How many flip-flops will be required? Decade means it can count up to what? In this way, it will count up to what? It will count up to decimal 9. Okay. After that, once it is becoming 1010, it will be reset to 0. This is instantaneous value. Okay. So 10 different values, binary values will be the output of this decade counters. As you can see, these are the values, output values. It means every counters here are having 4 flip-flops. Okay. From the counters, you can latch the values from those flip-flops into 4 flip-flop or latches, and can be given to the 771 decoder, which will drive the 771 display. Here. The latches are then decoded by 771 decoders to drive the LED displays as units, tens, and hundreds of counts. We can begin a conversion cycle by pressing the manual. This one. We press it, then press it will be giving a reset command to RAM generator as well as counters. It will start counting from 0 onwards. Initial value will be 0 of the counter as well as of this RAM. Refer carefully to logic diagram and waveforms. Manual reset resonates a reset pulse, and that clears all the decade counters to 0. Outputs are 0. And reset the RAM generator to 0. Initial value here is 0. Since Vx is positive, this is assumed to be positive. Okay. So here it will be positive output. Vc will be positive. This voltage enables the clock gate, allowing the clock CLK is getting connected here, and counter will start counting. At this point, time T1, I mean to say, here you see it is rising up to this T1. Its value is Bx. At the point when T1 is reaching, at T1, when Bx, RAM value is reaching Vx, this will fall. Okay, this will fall, and hence no clock will go, and it will stop counting. And its output is driving these flip-flops, and these flip-flops are driving the 77 decoder, and then finally the digital value is displayed here. Shortly thereafter, reset pulse is generated by the count logic. I mean to say, This is the control logic box that resets the ramp and clears the decade counters. And another conversion starts. Once counting is over, the output of the counter is latched into it. Thereafter, it is available for driving this. Then immediately, what will happen? This control logic will be sending a and another conversion will be started. Reset will be generated by this. It is 0, and all are 0, and start. But previous value, digital value will be available here to drive the LEDs. Now dual flow is similar to that, but it is more expensive because see that this is one here, compress here, integrator, comparator, and then control logic, and more or less here you see that time will be required more. First, the integrator is integrating from 0 to minus BC, then it is further integrating from minus BC to 0. So conversion time is double. But what happens is it is no more dependent on this. Okay, this will be cancelled out. Okay, it will be cancelled out, so it is independent of RC. That is the advantage. So let us see what is given here. The logic diagram is shown here, with the exception that the RAM generator and the comparator, the circuit is similar to the single slope only. Okay. In this case, the integrator forms the desired ramp. In fact, two different ramps as input switch to unknown input. First, it is applied to the unknown analog signal. Then it is ramped down to minus VC. Okay. Because integrator output is negative. That's minus VC. Then from there, if you put into this VREV, which is changed to VREV, reference voltage, then it ramps up in this direction and becomes 0. That's how it is said here. As the input switched first to the unknown input voltage Vx and then to the reference voltage Vr, here is the discussion for its operation. We begin the assumption that the clock is running. This clock generator is continuously generating the clock. Clock is running, and that input voltage Vx is positive. That is what is assumption. This input voltage is a positive quantity. A conversion cycle begins with the decade counters clear to all zeros. The RAM reset, and hence you get 0 volt here also. RAM generator output. Let's see. And the input switch to the unknown voltage Vx. It is connected here at this point to this switch. Since Vx is positive, the integrator output Vc will be a negative quantity. Okay. And this is what you will get negative value, minus Vc. The comparator output Vz, this is the Vz. It was negative, so it will be positive now. It is inverting. We allow the ramp to proceed for a fixed time and time period T1. Okay, this is the time period from here to T1. Determined by the count detector for time T1. For time T1 count detector, this is the count detector. Okay. So the actual voltage Vc at the end of the fixed time period T1 will depend on the unknown Vx. It will depend on the unknown Vx. Since we know that Vc equals to minus within parentheses Vx by Rc into T1 for an integrator. So we are talking about integrator only, which already you have seen earlier also, today also. When the counter reaches the fixed count at time t1, this counter reaching up to certain count value. The control unit is the control unit generates a pulse to clear the decade counters. Means it is going to clear to all zeros, and switch the integrator input to the negative reference. I mean to say, a reference voltage here it is negative. It will be like this. Yeah. The integrator will now begin to generate a RAM beginning from -VC, this point, to rise like this towards 0 and increasing steadily upward until it reaches 0 volt. All time the counter is counting and conversion cycle ends when VC equals to 0. This equals to 0. This clock gate is now disabled. Okay. Clock gate will be disabled at this point. Equation for the positive ramp is this one. In this case, the slope of this ramp is obviously V R by RC. It's a constant, but the time T2 is variable. In fact, since the integrator output voltage begins at 0, integrates down to -VC, and then integrates up to 0 volt, you can equate the equations. Given for VC. We have got two VC, no? VC is minus something, we have got, okay, and then VC plus something. Plus something is nothing but this one. Okay. So we can equate this. This is during T1 and this is during T2. The value of RC will cancel out and you will get Vx equals to VR into T2 by T1. And this reference value is known to us. And T1 is determined by the circuit, this control count detector. Okay. So clearly the unknown input voltage is directly proportional to the variable time T2. Means this is proportional to this because these two are known, other two, VR and T1. However, this time period is exactly the contents of the decade counters at the end of the conversion cycle. Is it clear?
Yes, sir.
Shubham Surana, is it not easy? So, the obvious advantage here is RC term, which cancel with each other. Here, this both side it is getting cancelled. In other words, this technique is free from absolute value of R and C and also from the variation in their values. Temperature, if varies the R and C value, then no problem. That term is not there for Vx. What is the time now? Should I summarize today or we'll take another class? This time is almost over, so we'll start summarizing this module and comparison between various converters in next class. Today we are going to stop. Let me check who are there and little discussion about the next page. Next class. Tomorrow we'll finish possibly, and then for quizzes and all I'll be contacting some of you. So Shubham Shurana, Pratham and all is there? No, absent. Okay, Shubham, you just confirm the date and time for quiz 4. And at the same time, you discuss the quiz 5 also, because we are going to end the module by tomorrow possibly. Okay. So another 2 classes are left over for us on 19th and 20th. 19th and 20th, because 14th is holiday, 15th is holiday. 15th we had a class, but that is holiday. And you are going to appear on quiz 4. So 19, 20, we may not take class, but we can conduct the quiz. So preferably on 19th or 20th, you should have your quiz, the 5th quiz. Shubham, are you listening to me?
Yes, sir.
So once you are deciding the time for the the 4th quiz on 15th, you decide for 5th also, because possibly that section also is going to complete the module, and then more or less you decide one date and time for the 5th quiz also. When your end sem will start, any news?